Yes, I think recording started. Well, hello again and welcome to our workshop. During these 4 days, as part of Digital Futures, we will explore performative design strategies for extreme conditions on Mars. So, today, in the introduction, Ozan will start by mentioning the schedule of the workshop, including the general concept of all of this. Thereafter, we will meet each other, starting with giving information about who we are. Afterwards, I will discuss the literature in the field, starting with the Earth, including some dark facts about climate change, and then possible solutions regarding performative strategies. And after that, we will continue with Earth and its extreme environments, including arid and polar deserts. Finally, we will enter the space territory, starting with the space architecture, the ISS, Mars, and future in space. At the end, we plan to discuss general inferences about the subject. And this is the schedule, and I am muting myself.
Welcome all. We will go over with the schedule of 4 days, and we will start today with the opening lecture from Gizem Hoca, and then we will give some information about the project, which will be on the Mars habitat. So we will introduce you to some tools so that you can simulate how the living on Mars would be like, and we will get the data from the simulation tools that we will be introducing in the second day, and then we will use Python, and then we will process these data to get some insight about how we can make our designs to sustain the life in the Mars habitation, and then we will give the project itself, and we will use the data that we have analyzed via our software, and then we will make a computational model, a generative system, so that we can use those data to turn it into the architecture of the habitat on Mars. And then you will be working on your project. You will be analyzing data and then turn these data into valuable information, and then use those information to control your parametric or computational models. And then you will be generating your habitats on Mars, and then we will combine your models in a shared model so that we can visualize and share our work together. So that's overall the process for 4 days. And I think we can start introducing ourselves, and then hear from your side so that we can know each other before proceeding. So, Gizem Hoca, would you like to start introducing yourself or myself? Okay, then I will start. I'm Ozan Yetkin, and I'm a researcher in the Middle East Technical University. We are conducting some courses in Middle East Technical University, including the digital design tools and methods. What my research area is about is the intersection between the software part and the architectural design. So most specifically, I'm working on artificial intelligence and machine learning. If you're interested in those topics, we can also discuss during the software development phase. But for this workshop, we will be focusing on the generative systems part of that mostly, and the data analysis part. I guess that's it.
So maybe I could give some information about myself. As you can see from the picture, it's a little bit old. My hair is not green there, for example. But if I start with myself, I am currently a research assistant and PhD candidate in the building science program at the Department of Architecture at Middle East Technical University. I started at METÜ as an architecture undergraduate in 2010 and have participated some competitions and projects during these periods. And now I am carrying out my doctoral studies within the framework of habitation on Mars. So Mars is my research field, I can say that. And during these 4 days, I think we will meet each other in a more intense way. So maybe you can start to introduce yourselves, and I will stop sharing my screen to see you. So who wants to start?
I'm Praneeth Tashne from India. So I'm actually going to do master's this year at IAC in IAC Barcelona. And I have deep interest towards space architecture. So a lot of competitions had worked regarding moon habitation, Mars habitation. So I had a lot of interest in that. So I find this workshop which can strengthen my practical aspect for the Mars or moon design that I'm aspiring for in the future.
Thank you.
Okay, I'm Sophia and I'm from China and I'm currently in Xi'an Architecture and Technology University and I'm major in architecture. I'm looking forward into the future and I also have experiences in interaction design and something about computer design, and those are all the fields that I'm interested in. And I'm really excited about this workshop because I think, yeah, Mars and the habitation is really excited, and I'm really happy to be with you guys, and I'm eager to learn everything about it. So thank you.
Thank you.
Hello. Yeah, so I'm Mohammed Saifis. I'm from India. I'm currently in London right now. So I did my master's in machine learning urbanism at the Bartlett School of Architecture, UCL. And now I'm pursuing my master's in international business management. And I've always been interested in space architecture. I've also taken part in some of the competitions before, and also attended one of the DigitalFUTURES workshop, which was related to moon architecture before. So it's a field that I'm very curious towards, trying to understand about the unknown and explore different landscapes. My sister is pursuing a master's in astronomy. So this is kind of a field of interest that we both share, and we're working on projects together. So I'm excited to learn more about it. So happy to be a part of the workshop. Thank you.
Thank you.
Hello. Can you hear me?
Yep.
Yes,
Hello.
I'm Yasaman. I'm from Iran, and I'm an architect. I'm really interested in some topics, including AI, machine learning, and also spaces, and some projects like that one that Elon Musk is working on and making humans multi-planetary. So I found this workshop really amazing. I wish that I can do well in this workshop. And I'm really glad to have this opportunity to be here.
Thank you. Thank you for your interest and sharing your information with us. Maybe I can bore you with the literature. I am starting. So I'm sharing my screen. I hope we'll start now. It start from start. Okay. Okay. Well, first of all, I want to start with the climate change and its dark truths. As you all experience, drastic change in the climate is affecting, and the extra heat is driving regional and seasonal temperature extremes, reducing snow cover, intensifying heavy rainfall, and changing habitat ranges. Many land and ocean ecosystems and their impact on their environment have all. I reached some real photos about these changes, but I couldn't put the real catastrophic photos on the slide because my heart couldn't take them. Yet the ugly truth is that the loss of some ecosystems have long-term or irreversible effects right now. So, on the other hand, several measures have been tried to be taken by countries like the Paris Agreement or COP26 and some sort of forecast about this issue. However, although we have made some progresses, we are not even close to the set targets. The current state of the world, desertification, drought, and unexpected temperature changes show that humanity is about to reach irreversible points. And one of the reasons of the climate change is actually excessive energy consumption. And the energy consumption rate of the structures increase approximately by 1.3% per year, which is greater than the worldwide annual population rate. And in other words, we are consuming more than we need. And also, 20% of the global energy is used up by only the commercial and residential building sector. So as a solution to this problem, the use of renewable energy is increasing day by day. And there is a growing evidence of the broader impacts of the shift towards renewables. And it's predicted that renewable energy will be increased to almost 30% this year. And photovoltaics and wind provide 2/3 of it. Moreover, solar energy is the most widely available resource for Earth, also other applications. And when changing climate is considered, humanity needs to develop a new generation of durable, low-impact structures in harmony with the environment and powered by appropriate renewable energies. For this reason, it is necessary to examine suitable performative strategies carefully. Well, I'm entering the literature right now, and starting from the 21st century, guiding design principles of architecture have been mainly influenced by performance. And several definitions were made about the subject. As you can see, one of the first definitions made by Gibson at the CIB's Commission meeting W60. From this definition till now, performative strategies have been adopted, altered, and used for the applications of the building performance methods. And the quantitative measurements of the architectural performance can be carried out with the simulation technologies. In addition to these simulation technologies, algorithm-based studies have gained an essential importance. However, whether the method of the performative design strategy is simulation-based or algorithm-based, one of the significant obstacles of this method, and as well as its most vital potential, is the identification of different performative features in a given project, creatively, carefully, successively balancing opposites of these performance goals. Yet, It's necessary to keep in mind that performative architecture is not just about coming up with useful answers to a group of fundamental problems. Therefore, it's needed to be analyzed deeply with its subheadings, which are defined by Xi as aesthetics and cultural performance, which is examined from and environmental performance. Well, among the three performance criteria defined by Xi, a structure's aesthetics and cultural performance is the most difficult to quantify because it includes assessments depending on personal preferences, actually. On the other hand, some of the factors in this category are open to rely upon measurable aspects, such as form shaped by functional requirements. Therefore, this subheading was discussed around the form finding action shaped by functional requirements. Function allocation is a fruitful way to form finding solution, actually. The evolution of the interior design of space habitats, which mainly follows the activity function distribution, can be observed from previous and current form design examples of space architecture. In general, the internal layout of these structures is shaped by the functional demands of the team, such as working, cleaning, preparing, and consuming food, along with the other demands. While these are shaping the formal language, they needed to be correlated with each other regarding to operation of the function and its relationship with the user and also the privacy. Accordingly, several methods has been developed, like bubble diagram, adjacency matrix, or space syntax theory. The bubble method that is frequently used in many architectural projects and helps to see the dimensions of the spaces needed for various activities, their adjacency and relationships between each other. Like the bubble diagram, adjacency matrix is also used as a tool to understand the linkage between functions to shape form. Adjacency matrix can be defined in general as a diagram to find out the relationship of activities regarding the initial needs. Therefore, privacy need could be used to zoning the functional adjacency. To illustrate, crib quarters require more private spaces where could maintain quiet places. Another method to correlate the function is called space syntax theory, which can be defined as the social performance of the buildings, and aims to provide a framework for understanding their possible human impacts. The syntax enables designers and researchers to build and assess their work by triangulating the enhanced link graph. Designing the habitats in space context has been mainly focused on optimization of the habitat due to problems related with logistics, times, and cost of long durations. Therefore, in the space settlement context, size of the function regarding volume and efforts to produce emissions in safe and efficient way. Structural systems have several criteria to be able to meet the required needs. However, when designed for a space habitat, these criteria should be differentiated from Earth conditions. For example, these structures must be designed considering four main loading types, which are reduced gravity, internal pressure, thermoelastic loads, and micrometeorite impacts. Earth and Mars are opposites when it comes to magnetic fields and atmospheric thicknesses. Thus, the planet would be exposed to harmful radiation. To propose a solution to that problem, the structure type and material of the structure are essential. For this reason, different types of structures were made, and among those studies, inflatable structures have become more prominent than the other ones. Additionally, using in-situ materials such as Martian regolith and its combination is another prominent solution for the material selection. And the environmental performance of a structure has a strong relation with the effects of environmental factors on the service systems. Well, sustainability and the maintenance of these energy needs is critical to ensure the continuity of the service systems. The sun is the source of practical all energy resources on the planet and also in the solar system. And solar radiation might be turned into a beneficial energy resource to lower the energy load of all settlements, both on Earth and other celestial bodies in the solar system. One of the exciting research about the harvesting sun in this space is origami-like PV system, as you can see from the bottom picture. The process of this system have been planned to test on the ISS, and these photovoltaics occupy less space while they are carried. Then when it's placed and set, they start to open like a flower with the help of its origami-inspired structure. Well, performative strategy subject is ended with this slide. Then I will continue to talk about extreme environments. And this part is a little bit National Geographic documentary. So we will coming to the documentary part right now.
Maybe before proceeding, I can interrupt at that point and ask if you, what do you think about the performative strategies or computational part of the system? For example, if you know anything about the performative strategies, not in the Mars context, but in the other contexts, what do you think about them, or any other feedbacks from the contextual part of it? Like, do you have any experience in environmental considered design or sustainable design in the other context? If you have such comments, you can always share them, because we can always adapt our code so that you will have fun. Anyone would like to come? Sorry?
I have a doubt regarding the like habitat. Like usually when we see extreme environment scenarios, people are wearing suit, or there is a very much covered room like that. So is there a way where we can, be free of the suits? For example, if we take Mars scenario, we need to wear a suit to move around, a space suit, and the kind of like, can we kind of change the like, can we have something like an invisible kind of shielding that can be done, or anything as such, just to avoid space suits like that?
I see. I think there are some methods in the discussed, so that I guess it will be available in the future. The way to avoid such spacesuits or any constraints that we will face in the space habitat is about having complete structures in the outer space. For example, if we have to make an artificial atmosphere, so that it means that we have to build a superstructure on any outer space. I guess ISS could be one example, so that we will not be needing those spacesuits or any other constraints, because if you take the ISS example as a superstructure, inside the ISS you can always wear as if you are in the Earth, right? You will not need a spacesuit in that case. But for the Mars case, it's a great challenge still, because we haven't built anything yet. So we have to understand the conditions in its very extreme, so that we can have some strategies in designing it. So the second and third day will be totally about that. But thanks for the contribution.
So is there any comments or questions?
Yeah, I would like to add something. So I had a small experience making inflated structures. So like in that kind of a situation, you consider the variations in gravity load and also the atmospheric pressure, like to control the inflation, like of the like like habitat structure, for example. So I think that's far I've got with trying to control the like environmental impact on, like, let's say, structure. Was it something like this that you were asking in terms of? Yeah.
Actually, the inflatable structures are very powerful solution for most of the space constructions. And also it's actually an performative action because in these sort of structures, we are trying to understand the environment and act as more suitable way in order to maintain the inner comfort. So actually it's an performative action.
Okay, thank you.
These issues are very interesting for me, so sometimes I get very excited and I couldn't stop myself, and I am just going on to explain what is it. If you have some sort of questions or if you don't understand anything, please stop me and ask, because I will just go on. So
okay. I have a question. I didn't quite follow about how to deal with gravity. You know, I didn't quite understand how these structures, yeah, deal with, you know, I don't know, anti-gravity or something.
Actually, it is changing from celestial body to celestial body, because when you think about ISS, it's microgravity. So it's nearly zero, and it's very challenging for all of the astronauts and the researchers in there. But for the planets, for example, in Mars, we will just search for the other. Actually, we will look for the numbers of the forces. It is different for the Mars, and it's very different for the Moon also. So in order to understand its actions, I think it was there. I will go. Yes, the reduced gravity is very interesting force when we think about and when we compare with the Earth, because when we think about Earth, it's our normal, and we know that it's, I don't know, G is equal to 9, something like that, some number. And when we think about these other bodies, they are different than, and its effects of the structure is different from the other ones. So we have to consider how to react with these reduced gravity. I was trying to say that. I'm not sure if I could answer the question. Sophia?
Oh, sorry, the internet has some conditions. I don't know, it is probably my problem, but yeah, I hear it's like, I didn't quite hear clearly, maybe because of the that condition.
Maybe I could explain a little with less words right now. Our gravitational forces is different than other bodies and also the ISS. So while we are trying to construct a structure, we need to consider these different forces. Actually, it's mainly about that.
Okay.
And then, should I continue? I am continuing. Section, we are still on Earth, and arid regions which are examined under the 3 subtitles with subtropical, coastal, and interior deserts. Also, polar regions, including the Arctic and Antarctic regions, were examined. Well, subtropical deserts cover almost 15% of the world. The majority of the subtropical deserts of Africa is covered by the Sahara. And in the vernacular architecture of Egypt, local building materials such as brick, stone, palm log, and wood are selected according to local construction techniques. Where there is not enough water to create the mud brick, the structures were made mainly with the stacked stones. Even though there are debatable approaches related to the following example, which is Old and New Kurna. One of the examples of vernacular architecture of the region is that complex that I say Old and New village of Kurna. Most of the houses have at least one inner courtyard and a terrace. Although making these courtyards and terraces is very easy on Earth, it is nearly impossible to create them on other celestial bodies for now. New Kurna, designed by Hassan Fatih, and he tried to use an Egyptian architectural language. The geometric forms of Coptic architecture with the mud brick construction techniques of Kanuz and the cemetery walls and domes of Nubian architecture are the prominent examples of this model. And also the structures in New Kurna consist of repeatable modules. So these repeatable modules create mainly modularity, like in space structures. And when we pass the coastal deserts, or with the other name, foggy deserts, are not like subtropical ones. They are located near the water and contains westerly fog, but they comprise scorching and arid lands. The 2 largest coastal deserts in the world are Namib and Atacama deserts. Atacama is considered as the driest non-polar desert in the world, and many Mars experiments are held in that desert. In this region, buildings comprise a shadow envelope for protection from intense sunlight. On the other hand, they were built compactly and inwardly, with thick stone or mud brick walls to store the internal energy released at night. Some of the exemplar buildings of Atacama Desert are in San Pedro de Atacama. I'm not sure the pronunciation is right or no, but it's like San Pedro de Atacama, I believe. The complexes includes adobe houses fenced by transversely placed adobe walls. In addition, the complex includes courtyards and corridors in which large adobe blocks and stone materials are used together. Well, unlike the subtropical and coastal deserts, the deserts are cold deserts. Mongolia and China include many of the world's interior deserts, and Gobi is one of the largest examples of these kind of deserts. Although lately mud brick, red brick houses and tile roofs can be seen in the region, Mongolian nomads often live in yurts. Yurts are built as well-weighted and lightweight structures actually. And these structures can be correlated with inflatable, flexible composite structures like the Transit Habitat or Transhab project designed as a space inflatable habitation module. In the yurts, tree branches are used for the frame and animal hair fats cover the yurt's trunk. The wooden tun located at the top of the yurt provides smoke evacuation and helps with interior lighting. The yurt has a circular plan, reducing the forces caused by wind. And the cylindrical body provides maximum enclosing space. And a hemispherical dome solves the problems produced by the precipitation. The interior temperature of the yurt is adjusted by the openings and the fuels burned in the stove, which is located in the middle of the yurt. And in the area, the government strongly supports the use of solar and wind energy right now. And actually, approximately 150,000 families in the region have started to meet their energy needs with small wind turbines and solar panels in starting from 2005, if I remember correctly. While we have already moved from warm places to cold ones, it is impossible without mentioning the polar areas, like the Arctic region. The Arctic region does not have definite boundaries, yet it's typically described as a region where it extends around the North Pole. It covers nearly 8% of the surface of the Earth and has over 4 million residents, which are human residents. Arctic districts and their vernacular architecture features vary due to the region's numerous different cultural, environmental, political, and social conditions, actually. One of the most known shelter is snow houses, or the other name, igloos, made of blocks of wind-packed dry snow. For the construction of an igloo, firstly, snow bricks are lined up to create a circle. Then the row of the brick need to be trimmed to form an upward spiral, as you can see from the second image. The snow bricks then are added with increasing inclination successively on top of each other until the desired dome shape obtained. The other example is the Tulu winter houses, constructed with cut sod, stone, and whalebone. These winter houses are built to resemble whales because actually they made up with the bones of whale. And the main room of the houses are constructed with a wooden structure. And the entrance tunnels of them are built with actual bones of the whale. And according to their beliefs, they were sacrificing actually these whales in order to eat them also and make these shelters for them. So in the opposite side of the Arctic, the Antarctic region comprises everything inside the Antarctic circle, including the Antarctica. Antarctica is a polar desert where being too cold for human habitation for a long time. Like the Arctic region, in the Antarctic region, at least one day with full daylight and one day without sunlight is experienced in a year. It does not have any indigenous human settlements. While Antarctica does not have any indigenous settlements, the continent is predominantly occupied by scientists. The first inhabitants of the continent built several huts. After for a while, the research stations have been constructed. One of them is Davis Station, which consists of 37 buildings. And these buildings have been in service since 1957 and had difficulty meeting today's needs, as you can guess. Therefore, VSP and Huberton architects started to reorganize the region. And you can see their conceptual drawing from this picture. And they agreed upon elevated aerodynamic modular buildings with open plan solutions with sustainable infrastructure using wind and solar power. In Seoul Station, by 2011, there were over 70 buildings in the station complex. And like the other station in the continent, most of the energy used by Seoul Station has been transported via ships. In order to diminish this transported energy and use renewable resources, they started to produce energy from wind and solar power. The Vassal Resource Station, the central Swedish station in Antarctica, was built in 1989, and the main building of the Vasa rests on 1.5 meter high pillars to prevent snow accumulation and is made of box plywood sections. As you can see from the examples, except the Antarctic region, in all of these extreme environments, vernacular materials have been used, and all of them use round shapes and modularity as survival mechanism. So, do you have any questions or comments about this subject? About these examples, or do you want to add some more examples about these extreme climates architecture?
I have a question. Is Mars like the combines of all these extreme conditions, or is more like some of these extreme conditions?
Actually, Mars like hell. So it is combined and more of these conditions because, for example, we have enough atmosphere here. We can go outside, but in Mars we cannot do that. And also some sort of different temperature changes make more problematic issues for the Mars also. But we can use some sort of elements from these extreme conditions, and we can apply them on Mars settlements.
Okay, thanks.
You're welcome.
Can we grow plants on Mars?
Can we?
Grow plants on Mars.
Actually, we can with artificial structures. For example, I will give some sort of spoiler for the project, but I just started, so I cannot stop myself right now. We can produce some sort of greenhouses for Mars. And in these greenhouses, we can create artificial atmospheres, so we can produce several plants in that greenhouse actually.
Like, can we use the Martian soil for that?
Actually, we didn't experience these kind of experiments right now. It can be possible, but probably for the Earth's plants, we need to combine some sort of different soil types with that. Because if I remember correctly, Mars soil contains a lot of sulfur, and it can be harmful for some sort of plants.
Okay. So bamboo is not possible then.
Maybe we can just alter these soil, so in that position we can use it as it is.
Okay.
If you do not have any sort of comments or questions, I will leave Earth and enter the space territories. So, Maybe we can give a break if you want. Because when I start space architecture, I cannot stop myself. So maybe we can give 50 minutes break. Is it okay for you?
Yeah, that's okay.
Okay, then we will meet after 15 minutes. I am pausing the recording right now and share my screen. So, yes. And let's start from beginning. Maybe we can just skip, then we can start space architecture. Well, as you can see from the slides, we just talk about the deserts and also the Antarctic and Arctic regions. Well, I will just set my screen. Yes. Well, humanity is trying to reach the height of cosmic civilization. And we owe our home, the Earth, a meaningful tribute to our beginnings by bringing the lessons acquired on Earth as we prepare to reach deep space. One of the first steps that may be made is to examine, to liberate space architecture from static survival productions and instead study dynamic sustainable space structures. From low orbit, from low Earth orbit to planetary exploration far beyond, self-assembled, flexible, and autonomously reconfigurable structures are the future of humans living in space. Space architecture has been architectural field for many years, but only in a narrow region, and it's mostly practiced as sketch problems, actually. In this respect, for many architects, designing a space station, a moon, or a Mars habitation is akin to playing in a science fiction field mostly. However, as you can see from the space architecture definition made by the Technical Aerospace Architecture Subcommittee of the American Institute of Aerodynamics and Astronautics, space architecture is the theory and practice of designing and building inhabited environments in outer space, to explore and occupy new places. Space architecture has relationships with diverse fields. As you can see from here, it's aerospace engineering, terrestrial architecture, transportation design, medicine, human factors, space science, law, and art. Well, from that slide, you can see the first space architect's hand drawings. These drawings made by Galina Balashova in 1963. Space exploration, which gained momentum with the Cold War and progressed with the country's efforts, started to progress with international collaborations over time. The first experience of living in space was gained with Mir Space Station, which is launched in 1986. And to understand the difficulties of establishing a permanent presence in space. So over 100 cosmonauts and astronauts from 12 nationalities have flown on Mir between 1988 and 1999. With the lessons learned with the Mir, the International Space Station was established. After being observed in the Mir and ISS, where people can live in space, the technological developments advance, and there has been a drastic shift in the space industry in the last decades from pioneering short-term exploration to long-term planning for habitation, and also new ventures such as space tourism. From that perspective, in space architecture heading, space and human habitation was examined under 3 subheadings. These are the International Space Station, where what has been done on the subject so far, habitation on Mars, which include the environmental features of Mars, and finally, future space habitats, covering the future predictions and proposed projects for outer space settlements. Well, the International Space Station was established in 1998 with launching the Zarya control module. However, building a space station dates back to Salyut 1, which is sent to space in 1971, and Skylab, which is sent to space in 1973. While architect Galina Bolashova was designing the interiors of Russian spacecrafts, industrial designer Raymond Loewy was designing the US ones, including Skylab. Today, aerospace predominantly driven by engineering and management practices. Although many fields in this area have been improved and into higher specialized, they did not focus on human needs, art, and design. However, when considering the design of the ISS, the modularity is the dominant approach. And on the International Space Station, the modules designed as cylindrical living spaces. Yet the ISS has many problems due to ignoring human needs. For instance, there is not enough space for inhabitants, as the racks and equipment occupy most of the area. Is an intense challenge. Inside the ISS, for now, the modules is not able to produce the essential stimulants of the terrestrial environment. On the other hand, these challenges actually should be used as design inputs and turn into opportunities. Well, the structure of the ISS is mainly consists of titanium Kevlar fabric and high-grade steel, which despite being light is sturdy and puncture resistant. The components of the station have to be light. Thus, aluminum is the most outer shell material, most common outer shell material for the modules instead of steel. In addition, the structure needs to be protected from debris impact with the help of layers of Kevlar, ceramic fabrics, and other advanced materials to form a blanket up to 10 centimeters thick around each module's aluminum shell. The ISS comprises an elaborate environmental control and life support system, which is subdivided into 7 parts, as you can see from the slide. These parts have different subparts that have been changed and modified numerous times over the years. However, the main components have remained to serve. Well, as we continue to Mars, Mars is one of the most examined planets in the solar system. When combined with the continuing observations from Earth, the collected data has resulted in a detailed picture of Mars. In its current state, the mass of Mars, regarding the amount of matter, is 1/10 that of Earth. While 6 Mars volumes could equal to 1 Earth volume, the Mars is approximately 71% as dense as Earth. On Mars, a person would experience almost 63% less gravity than Earth. Despite the solar irradiation of Mars is nearly half of Earth, Mars has the potential to harvest sun. 2 planets have similar tilt of axis, which means that similar seasons would be experienced on Mars. So, yay, there's spring on Mars. But on the other hand, the seasons are more extended than Earth, as Mars completes a year nearly twice as long as Earth. Additionally, Due to the elliptical orbit of Mars, the duration of some seasons vary in the northern hemisphere and the southern hemisphere of the planet. But although the seasons have the similarities, these two planets are not similar in terms of average temperatures. Mars is much, much more colder than Earth. One of the significant differences that will affect life in the most is the variation between the atmospheres of these two planets. According to characteristics and approximate compositions, the atmosphere of Earth is over 100 times denser than the atmosphere of Mars. The thin atmosphere of Mars can cause several outcomes, like temperature differences in one sol. Sol is the name of one day on Earth, on Mars, and high radiation levels is the other outcome. While the temperature within a potential future habitation should remain constant, the temperature differences between inside and outside fluctuates dramatically during a sol. Extreme temperature variations results in huge thermal loads, which significantly impacts the stiffness of potential structures, actually. And for the space habitation feature, we can reduce payload weight for a given volume, minimize construction complexity, and explore transformative space structure adaptability without just relying on astronauts' extravehicular activities and using only fixed hard shell systems. New missions designed for the in-space buildings are possible in the light of the paradigm shift, which has been going on for years and can now show itself with approaches and methodologies of recent studies. The prominent vernacular space architecture shapes its vocabulary from a modular kit of elements. And its first example were applied in the habitat could be categorized under three headings: pre-integrated, prefabricated, and in-situ constructed. Using experience in extreme environments on Earth, such as the deserts, polar regions, and also like ISS, we space architecture. Organizations, competitions, and workshops establish to gather information and produce new ideas related to the topic, like the 3D printing building blocks for lunar habitat project for ACA conducted by Foster and Partners in 2009. In the Foster and Partners lunar project, class 2 and class 3 were combined with foldable bays, which will be transported from Earth, and use of lunar regoliths with 3D printing techniques. Like the studies examined for Moon, researchers analyzed habitation solutions for a long-term stay on Mars, and these studies were mainly focused on form, structural challenges, and constructional materials and techniques. If you want, I can give more examples about this issue in the following days. But from now on, do you have any kind of comments or questions about the subject?
Ma'am, why is the glass very small, like for the buildings there? So, is it like structural problem or cost or anything as such?
It's mainly structural, actually. For example, pre-integrated one is the class 1 is produced on Earth and carried with the transportation vehicles, and then just put it in the other planets. For the class 2, it is prefabricated but not connected, and it's connected in the celestial body. The in-situ one, the third class, is mainly use the vernacular material of the planets, and such as regoliths and the other kind of materials that we found in the planets.
No, I'm asking glass.
A glass. For the glass one, probably it's mainly will be pre-integrated in the most part of the settlement issues, because it's need to be fabricated. So if we can able to create some sort of factories in the where we go, we can produce these.
Is there a certain glass that's used for space housing?
I believe I will just go to the ISS slide, because I think there is some sort of layering in here. Can you see my mouse?
No.
Maybe pointer, yeah, from here.
Yes,
For
yes,
example, in the ISS, they are using these layer system for the glass.
okay.
And maybe I can search for more information for tomorrow, and we can look at them also.
Yes. Thank you.
For the light issues, there were some competition outcome. They created a habitation with ice, and they tried to solve this issue with the material of ice. And it's a little bit utopian, but it's a solution.
But won't the ice melt on Mars? Like radiation, sun radiation?
Yes, for the radiation issue also we can use ice. They comment on that issue, so they created the solution with that ice issue. So, is there any more comments?
That's from my side.
Thank you.
No, I think we can go
Proceed.
ahead. Yeah.
Okay. Actually, we are in our last slide. Well, in today's architecture, the ISS, Mars, and what do you think about the subject discussed till now? And also maybe we can discuss about these questions. For example, what do you think about what are the main needs for a space habitat?
Oxygen.
Of course, yes, doğru.
Maybe water.
Yeah. Maybe we can ask this question from more architectural or structural point of view. What can be main needs about this issue?
Like, can we design the spaces more bigger? Because when we see a lot of renders or concepts, the spaces are very tiny, and people might find it claustrophobic. So, can we like expand the structure a bit more?
Actually, it is the small spaces caused by the environmental factors and also the money issues, because when we create some sort of settlements or habitation, it needs a lot of material and also financial support. And when we think about these extreme conditions, the compact solutions are more preferable.
Okay. And for Mars, ma'am, if the Mars soil is suitable for growing plants, like if it's suitable to grow bamboo on Mars, wouldn't it solve a bit of the structural requirements? Like we can use it for the structural design of structures there, like a framework.
For the structure, they were trying to actually use Mars regolith also without considering about the plantation. But if we can create some sort of food process with the Mars soil, it will be probably the very excessive success, because it will solve a lot of problems in there.
I have a question. In the prayer example, are they print these materials and assemble it on the Mars?
For example, for the lunar one, they create a base carried from Earth, and they put it in the moon surface, then added the inflatable structure. It was more compact when they put it there. So they just inflated, and they covered surface of the structure with the moon regoliths. So actually they used all of these technologies. For that one, it's very similar, but there were no kind of surface for the base, but they printed out with Mars regolith these outer shell.
Yes, I mean, because the gravity is very little, I mean, is there gonna be some problems when assembling all these projects?
Yes, these assembling mostly taught by this assembly will be done with some sort of robots. So they were thinking that they will just go there and robots. I'm not sure if some sort of robots in here showing, not, but we can just look at afterwards. And these 3D printing issues are made in there. As you can see from here, for example, for the air, they thought that they will be an printing machine there, so it will structure with the Mars regolith and use that 3D print. And ISS, they were experimenting at these issues, and they started to success about the 3D printing subject.
Okay, thanks.
So, what do you think about the gathering around the architectural and engineering perspectives?
Yeah, I think powering the settlement is also important. So we need some kind of infrastructure that generates electricity, like probably solar. So that also have to be incorporated within the settlement thing.
Yes, for this issue, actually, for example, in these settlements, for example, for the Mars, we cannot use wind because the atmosphere is very thin and we cannot reach to produce an energy from wind with that atmosphere. So actually we rely upon solar power for this issue in the first place, for example.
Okay. And what about like geothermal or something of that sort? Is that a possibility that can be explored?
I think my internet is not that much good, so I couldn't understand the question.
Yeah, I was wondering what other energy sources could be. Like, could geothermal be another solution?
Actually, geothermal may be used by in settling is done, but I know that they are using some sort of nuclear energy for the orbiting vehicles that are sent to the Mars.
Okay, all right. Thank you.
I want to know how to resist the extreme cold weather condition. Is there like a heating system or something like that?
Actually, it's a very important problem for these issues. For example, in the ISS, as you can see from there, there's a lot of environmental environment control life systems for this issue. As you know, the temperature is very different from Earth, so we need to maintain some sort of balanced temperatures in these these spaces. So there's a lot of need for storage space, and there's a lot of need for the energy to maintain these sort of temperatures.
Okay.
So going Mars is actually, there's a lot of work there.
Yeah. Also, I was wondering, I heard there are a lot of craters on the ground of the Mars. So maybe the ground is not very flat and there are lots of sandstorms. So should we take all these into consideration as well?
Actually, sandstorms are exaggerated because of some sort of science fiction movies. It's not that much harder in Mars because atmosphere is not that thick in there. Yes, there is accumulation of sand because of the radiation from sun, but it's not that much powerful for example, just broken to antenna of a vehicle.
Okay.
It's affecting vision and it's covering solar panels. It's a problem for that part, but it's not problem for the actual living. So maybe we can talk about what sort of performance strategies we need in there. Actually, we talk about a little bit, but do you have any more issue? Because as Ozan Hocam said in the beginning of the lecture, we can alter about these issues, what you want to add to project. Well, I think you do not want to talk. Okay.
No, this is kind of thinking, processing it slowly.
Of course. Of course. Then maybe we can just, maybe as a final remark, I can finish that lecture with a quote from the Hitchhiker's Guide to the Galaxy, which was my favorite books. The quote is, "Space is big. You just won't believe how vastly, hugely, and mind-bogglingly big it is." I mean, you may think it's a long way down the road to chemist, but that's just peanuts to space. So we have a lot of work to do about this issue. And thank you for your attention. Maybe I can stop sharing my presentation and maybe we can give a break if it is okay for all of you.
Yeah, I think so. Okay. I wanted to ask about, about something that I found interesting is that if we figure out solutions for extreme conditions like Mars, I think it'll help us a lot in even coming up with innovative solutions on Earth.
Of course.
So even if we might, like the chance of the implementation doesn't happen right away, but in the process of our research, we would, of course, I think, figure out solutions for conditions on Earth. And I find this interesting.
Yes, I believe it's very interesting issue also because, for example, most of the experiments held in ISS actually help to Earth, and because of that, actually, I started with Earth because when we create some sort of extreme solutions for that kind of environments, it's very suitable for Earth also, and Earth our home, and Earth is our home, so it's very useful for all of us.
Yes, yes, that's very true. All right. So after the break, do we meet again?
Yes.
Okay.
Yep. Are you excited for the programming part? Because I can give an introductory lecture for the programming. And then from that point, starting from tomorrow, we can get our hands dirty and start coding.
All right. Yes.
Okay, great.
Yeah.
Okay, then let's meet in 15 minutes and start the programming lecture, the introductory part, and then I can provide you some resources so that you can start learning Python if you don't know anything about it. There's some really beginner things, or if you already know some sort of programming or Python language, you can always go to the resources that have more advanced things. Okay.
Okay. Thank you.
See you in 15 minutes.
Okay, I want to ask, do I need to download some software now or maybe later?
For today, no, but if you want to try, there are some online Python interpreters that you can start coding and run on your browser. Or, but if you need to dig more, we will also use some online tools like Colab or Kaggle tomorrow, so that you will be running your Python code on your browsers. No need to install anything, but if you need to dig more into programming, of course, we can recommend some tools that you can download and start coding more in a more advanced way. Okay.
Okay, thank you.
Great. Any other questions before we proceed to the break? Okay, then. See you in 15 minutes. Tomorrow we will continue with the Python part of it, and then we will do some hands-on exercises together tomorrow, and we will see an example of how to process data in Python, and then it will be obviously about your project, and then we will move on to the visual programming, and then to the generative part of it. We will use the data from a simulation software. We will process the data with the Python, and then we will use the processed data to generate our habitats on Mars. I will start with the very fundamental parts of it. I hope you can see my screen without any problem. Yep, no?
Yes, we can see it.
Great. So I will go over with the fundamentals of the programming. But before proceeding to the Python, I will mention about the really basics, and I will start with the computer itself, because it's really fundamental to understand what a computer is and what it does. And then we will do this part today, and then we will move on with the Python part of it tomorrow. And you can interrupt me at any time so that we can proceed, because it's really important to understand what a computer is and what it does. And the computer is a basic device which is capable of performing computations. So computation means making logical decisions, but the thing about the computers is it makes the decisions at speeds of millions or even billions times faster than us. So think about 100 lines of code and think about yourself summing them up. It would take a lot of time if you do it manually, but thanks to computers, we can do it in a really fast way. And computers basically process data under the control of sets of instructions called computer programs. So what we will do is to give sets of instructions to the computer so that it processes the data, and then we can derive some information so that we can we can decide on the architectural parts of a habitat on Mars. So the basics of computer is about 3 parts. The first part is the computing units, and the second is the memory units, and the most important part, I guess, is the connections between the computing unit and the memory unit. And the computing unit is basically the processor, like M1 chips in MacBooks or i7 Intel chips on Windows laptops. These are the computing units. And it's about how many computation a computer can do in 1 second. And the memory is the RAM. Basically, it's about how much data a computer can hold, and it's about how fast we can read from it and write to it. So if maybe you have heard of SSDs or HDDs. So SSD is a new technology in which you can speed up the writing and reading the speed of the memory unit. And the connection between CU and MU, the CU is the computing unit and MU is the memory unit. It's about how fast data can move from one place to another. So it's about the transferring data from one place to the other. And the basic part of programming starts here. So as I told you, the most interesting part is the connection between the computing unit and the memory unit. So it is the memory unit and this is the computing unit. And every program that we write and build is lying somewhere here. And when you're really close to the computing unit, you can see that it's the fastest way to do such things. But if you move towards the memory part, your program will become slower and slower. It's called a high level and low level in programming, and it's really a really important topic. And Python is somewhere in between, but it's more close to the slower part. And there are some advantages and disadvantages to it. As you move closer to the computing unit, the language, the syntax of the language becomes hard. So it is that these languages like assembly or C or Java is harder to learn than Python. So that's the basic thing about the high level and low level thing. And the programming is a sequence of instructions that specifies how to perform a computation. So never forget that computers are really stupid. You have to tell each and every instruction to a computer in order for the computer to do a task for you. For example, if you tell something to a human being, it's really easy for a human being to understand you and take some action. But it's really hard to give the computer some instructions. It's about writing each and everything. And if you forget a simple thing like semicolon or a comma, the computer will having hard time understanding you and completing your set of instructions. By the way, is there anyone who have experienced any kind of programming before? It could be Grasshopper, it could be anything.
I have some basic experience about Grasshopper, but I don't know if it will become a help to this project.
Great, that will be totally helpful because after Python, we will proceed to the Grasshopper in order to generate our geometries about the Martian habitation on Mars. We will use Grasshopper, but before proceeding it, we will need some Python because we will use a simulation tool, and we need to process the simulation data to calculate, for example, how much space do we need for it for the greenhouse.
Okay.
Okay, great. And the basics part. But before proceeding, I need to show some sequence of instructions from that simple diagram. These are called pseudocodes or workflow or flow diagrams. I guess you're also using it in the design process because these are really good tools to visualize your overall process, whether you're writing a Python program or designing a building, it doesn't matter. It is a great way to tell someone or show someone the process or underlying principles of your decision. So it's the really same way when it comes to programming. And for example, here you can see that process starts from here and we proceed to a decision. And based on that decision, either we say we get yes or no. If we get no, we end the process. If we have yes, we continue. You can think of it like having a program that checks the oxygen level and say that if it is suitable for a human being to survive. For example, you can write a code to check and monitor the oxygen level in the Martian habitation or outer space habitation. And it can give you feedback of, for example, if the oxygen level goes below that meter cube, you should increase the oxygen level, or you will have hard time maintaining the life inside that habitat. You can think of it like that. And we will see tomorrow the overall decision chart of a program that handles the simulation data about the Mars. Okay.
Okay.
Yep. And the basics of programming is really simple. I think that you are also familiar with such concepts because we are using it in our daily lives, like input. The input is the data we get from the keyboard, from a file, or some other device. For example, in the outer space context, it can be the Curiosity rover that hovers in Mars and gathers some data about the soil, about the wind speed, or dust particles. These are the inputs, and that's how we speculate about how to make a habitat from Mars. Thanks to those devices and thanks to those inputs, we can process those inputs and say that, oh, the gravity in Mars is something like that. And the other crucial thing is the output, which is the display data on the screen or on the file or on other device. For example, we can set our programs to provide some output so that we can proceed, take them and analyze it, or we can send them to another program so that it will be derived, it will be transformed into a valuable information. And what lies between input and output is the operation. So you can think of it like that. We have the input, we have some operations, and we have the output. So operation is something in between the input and output. And it's like performing basic mathematical operations like addition and multiplication. It's not that hard. It's a really basic mathematical operations when it comes to programming. But of course, we have some advanced methods today that handles the conditional execution, for example. And the conditional execution is about checking the certain conditions and executing the appropriate sequence of statements. It's like checking the oxygen level at each day and say that if it goes below the survival limit, or if it's okay for human beings to survive in that habitat. You can think of it like that. And the other part is the repetition, and it's really the merit of programming, because programs are able to perform some action repeatedly and usually with some variation. For example, you can think of it like simulating a crew of 4 people sent to Mars, and repeatedly you can check their conditions and check for everyone that if they're okay with their oxygen level, if they're okay with the food that they have, or you can simulate some greenhouse data to see, for example, how much food they can produce in each day, and more like that. So the rest of them is about Python. I know that you're a bit tired for today, so we will continue the Python part of it after today. So tomorrow we will conduct the Python part, and we will do some exercises. So basically the programming is about that. Do you have any comments or anything that you want to ask or discuss about programming before we proceed to the Python?
Yes, I do. I wanna know more about computer programming and Python and do some preview. And because I didn't know much about it before, so is there some materials that you can recommend to me? Yes, and I can use my spare time to learn more about it, so I'll better accommodate tomorrow.
Yep, great. For Python, you can use those resources. We can also share it to the chat. Let me copy and paste it to the chat for everyone. So these are the resources for programming, the Python programming. You can always check. Code Academy is a bit more comprehensive. It takes more time. If you don't have much time, I would recommend checking to the Kaggle. It takes about 8 hours. You can start from today and continue for tomorrow. And since we have 4 days for workshop, you will have chance to finish all those exercises in Kaggle, maybe we can do it together also tomorrow. And W3 schools are for people who know the basics of Python, because it is like a handbook or a cheat sheet. It is like checking the methods, available methods, when you get stuck at programming. So if you don't know much about Python, you can start from Kaggle. If you have more time, you can start from the Code Academy's Python course. But if you know a bit about Python and you are feeling a bit comfortable, you can check to W3 School to see the available methods, and maybe doing only the parts that you don't feel comfortable about. But the most important thing is understanding the language independent part of programming. Like, for example, Google has some visual programming tool. I don't remember the name. Yeah, Blockly. Blockly is a great tool that you can discover about programming without doing any coding work. For example, there are some ready-made components that you can drag and drop your canvas, and you can run your program and see its output. For example, for example, we have move forward, and if you run your program, you will see that your character will move, and it's the JavaScript code for that. It's really easy, but things get more complicated. It has 10 levels in total for the maze, of course. But you can also discover some other things. I will also share this link in the chat. So if you experience with the Blockly, you will feel more comfortable about thinking like computer. So I strongly recommend Blockly to have some algorithmic thinking. Okay. Great. Any other things before we wrap up today?
No, that's it from me.
Okay, great.
Yeah.
Okay, then. I think we can wrap up today and start tomorrow again.
I also have a question. How advanced should we just how advanced should we be in the Python for the final project?
Don't worry about that, because we will use a shared code altogether. What you need to understand is not to writing the code part. Of course, we will do some exercises to make you feel more comfortable. But for this workshop, what you need to focus on is to understand how it works and how to run the very same code for your case. For example, each of you will have a different simulation data, and what you need to do is to run the very same code with the different inputs and observe and compare the output, so that we are good to go. But if you have some trouble during the process, we will be here to help you and instruct you about the usage of Python.
Okay. So for the final presentation, we only need to focus mainly on the seminar, or does it require some of our spare time outside the seminar to finish the work?
Yep. Also, we will use at the lecture hours. For example, you can try running your code and seeing the output during the lecture hours, and then we will be here to help you. So if you have some trouble about running Python or translating data from Python to Grasshopper, we will be here to help you.
Okay, thanks.
Okay, you're welcome. Any other things that you wonder about the workshop? Okay, then I will pass my words to Gizem Hoca to wrap up today. See you tomorrow.
Okay, bye-bye.
Well, thank you for all. So we will see you tomorrow at, I'm not sure which time you are. So we will see you tomorrow.
Thank you, ma'am.
All right. See you
Thank
tomorrow.
you. See you tomorrow.
Bye-bye.
Bye-bye.